So we saw that you can have a continuous map which is a bijection, but it's not a homeomorphism. Now it's very useful to be able to conclude homeomorphism from just continuous, and in the presence of compactness we usually can. So let me just state, but first it's worth having a definition. A map f from x to y is closed and equal, you have a corresponding definition as open if v open if v contained in x closed implies that f of v, which is contained in y, is closed. And in the case of open, of course, we need v contained in x open implies f of v open. So the image of an open set is open. It's called an open map. In complex analysis, you have an important result telling you that maps are often open in that particular context. And if the image of a closed set is closed, it's also this. And the following proposition is immediate. If f from x to y is a continuous bijection which is open or closed, either way, then f is a homeomorphism. Okay, so let's just say proof. The idea is that f of v is f inverse of v. I think this is put it very clumsily. So f of v is the inverse. It's not f inverse of v. Rather, I'll write it as f inverse of v, which looks too cryptic. So this is g inverse of v. That's what I mean, where g is f inverse. Okay. So briefly, if I have a function f from x to y, which is a bijection, then g is its inverse. And what we have to show is g is continuous. The image under f is the inverse image under g. So if closed sets go to closed sets, then you are continuous. And if open sets go to open sets, you are continuous. So as long as the map has an inverse, okay, so for open or closed maps, maps using different criteria for continuity, one the definition and one the closed set criteria, G is continuous. G, which is F inverse, is continuous. So far so good, and now this gives the theorem. Any function f from x to y. So continuous bijection, let's put it briefly. Continuous bijection is a homeomorphism. For many years, I should admit, I thought this is a weird statement put together just because you can, but then later on discovered that it actually comes up in practice quite often, that you verify this, because one of the spaces can be very concrete and it's easier to verify continuity in one direction. Say when we are looking at moduli spaces, whatever it is, it's much easier to verify continuity in one direction. And compact Hausdorff is continuous is a I forgot to write the main hypothesis. From X compact to Y Hausdorff. Okay, we show actually something more general. We show F is closed, and this does not require if F maps X to Y continuous, X is compact, and Y Hausdorff. I should have just stated this as a separate fact, though I have not actually seen this part being used by itself. So if it's in fact a more general fact that a closed map from X, a compact to Hausdorff space is a continuous map from a compact to Hausdorff base is closed. So namely, this is really easy. So if f in X closed, it's a closed set, subset of a compact space. So it implies f is compact, which implies that little f of the set f is compact because the image of y, and this is contained in y, and because y is Hausdorff, little f of f is closed. So image of a closed set is closed because compact sets go to compact sets. I should make a comment here. It looks like compactness is nicely preserved, but inverse images of compact sets are not compact in general. That's a special class of maps called proper maps for which that is the case. So we'll just see quickly that this hypothesis is really needed. The hypothesis of being Hausdorff. So example, if I take x to be an or rather s to be an infinite set, and x is s with cofinite topology, then this is compact. So in fact, even for a finite set, cofinite topology is always compact. This implies that X is compact. This is an easy exercise. We have an infinite set. It has an open cover. Well, the first set in the cover, just pick any one, excludes only finitely many points. And then you pick open sets which contain those, and that gives you your finite cover. Now suppose we take y equals s with this indiscrete topology. Okay. This is also compact, but not needed in the following statement. But we take f from x to y, the identity, by which I mean as a function on sets its identity. Okay. Then f is continuous, because onto indiscrete space, continuous and bijective. But it's not a homeomorphism. In fact, it's not a closed map. Not a closed map. Not a homeomorphism because it's not a closed map. Incidentally, this also gives us examples where you have, by looking at the proof of this, the Hausdorff condition is necessary for compact subsets to be actually closed. Because if you take an infinite subset of this set which is already infinite with cofinite topology, it will be compact because the restricted topology is cofinite, but it will not be closed in X.